So let's start this week, since you don't have any questions, it seems. So today let's go back to the plan. We're following the plan. We did not meet last week because there was a National Day on Tuesday, and this is our class, so we missed that, but it was taken into consideration. That's why we had some weeks, 2 topics at the same time. And yeah, so this week we're talking about functions, and we're taking the mini test 3. I just added, for clarity, which week this is going to be addressing, just to make sure that nobody gets anything wrong. So for example, today the mini test number 3 is going to be about the week 4, which is the sets and set operations, which is basically what you had the review, the weekly reviews that you had. This is the weekly review week 4, which is you had the sets and set operations. So we're following the same pattern, nothing new. We just keep doing what we're doing, inshallah. Hopefully things are going to be good, because you practiced enough to get the full mark, inshallah, on the mini test, and also to get ready for the midterm theory exam, which is going to be 2 weeks from now, inshallah. Now, what is going to be what are the topics that are going to be covered during this midterm theoretical exam? All above. So from chapter 1 until chapter 2.4, which is the last thing, sequences and summations. This is what we're going to be doing, inshallah, next week. I heard someone maybe raising a hand or writing something. Yes, there's supposed to be sound. I don't know if you're hearing me. Are you? So yeah. So maybe you need to check your audio. All right, so let me just put it here. Okay, so today we'll talk about the functions, which is, again, this is another simple week, because maybe the only new thing is going to be some of the definitions, but besides that it's going to be very straightforward, inshallah. So I used the slides again from Dr. Abdul Salam. However, I added some things and changed them, uploaded them into the resources. You can find the latest, always you can find the latest in the resources here. For those who did not maybe checked, I also added chapters, just sections of the chapters we're covering. And also at the end of the book we have these odd numbered exercises. So you can, if you do the exercise at the end of every chapter, the odd ones, you have the solutions to them. So exercise number 1, number 3, number 5, etc. All the odd numbered questions, you have the answers to them. And yeah, that's so this is the thing. Every time I update a slide, you can find it at the bottom, because I also add this date when it was updated, so you can always see that there. Oh yes, talking about this, I realized that actually I also uploaded another file called 2.3 functions with midterm answer key. So this is some previously done midterm exam. That's a good thing for you to review, but however, is it going to be exactly the same type of questions? Is it going to be exactly the coverage? No, the coverage, because I did not check if the coverage is covering everything up until 2.4. If it is, then it's the same coverage. If it's not, our coverage is from the beginning until the end, from week 1 to week 7. That's going to be the coverage for the midterm theoretical exam. Of course, this is going to be on paper, in exam rooms, etc. All right. So this being said, let's just jump right in. Now let's start by talking about the functions, and basically why do we need them. The idea is we would like to assign, like from a specific set, some elements from another set. Like for example, in this example we have, let's say that these are student names, and these are the possible grades, and we'd like to record the grade that each student got. So Anas got B, and also Basim got B. So we have different elements from this set, the set of students, and different elements from the set of grades, and we'd like to have some link, some transition from one to another, and this is a function basically. So a function is from, it takes something from, links something from a set to something from another set. Now this is general, of course, but we're going to go into some more detailed examples. So let A and B be non-empty sets. This is the definition. A function f from A to B. So a function is from one set to another set, is an assignment of exactly one element of B to each element of A. So each element of A has one element of B. But notice, I'm not saying that each element of B has one element of A, because as you can see here, this B is, you have two associations with it, one that is coming from Anas and the other one from Basim. So we're not saying that from B there's only one. So this is the set A, this is the set A, this is the set B. So a function from A to B is that from every element of A there's one in B. Anyway, there's some kind of special cases. We'll talk about the special case, but this is the definition, what it says. So a function f from A to B is an assignment of exactly one element of B to each element of A. So we write f A equal B if B is the unique element of B assigned by the function f to the element of A. So that means if f of A is giving you, f of A is going to be B, a unique element. So I'm just going to just skip some parts because it's a lot of just talking. I would like to go into the actual examples and so we can see them more in practical. But the general idea is that we have a function that starts from one set and it goes to another set. So it's also called mapping. We map elements from A to B, or transformation from A we transform to B, and this is going to be like the way how we represent it. F column A, and then this conditional statement B. But this is the way we represent the function. All right, and now another set of terminologies. And this is, as I said, maybe the difficult part of this whole thing is just we have a lot of different names that we're going to be using, and I would like to make sure that we just get used to them. Of course, it's the more we use them, the more it's going to be easy to memorize. So now the function, if we say a function from A to B, A has a name, and then B they have given another name, and also the element of A that is also have the, after we apply the function to it, the equivalent in B, it has also a name. So this is what we mean. So now let's understand. This A is going to be called the domain. So if I have a function from A to B, A is the domain. What about B? Is the codomain. All right, so this is about the sets. F is from A to B. That means this is the domain, and this is the codomain. Let's no codomain. There's no dash. So that's one thing. But A is, it has a lot of elements. It has some different elements. So if now I look at the smaller A, this is called the pre-image, because B is going to be the f of A is going to be called the image. So if we have, if f of A equal B, that means one element inside A, so this thing, so that element is the pre-image of B, and B is the image of A. So that's That's the thing. So we have image, pre-image. These are about the values inside the set. Domain, codomain is about, this is about the set themselves. The domain is from where we start, the codomain where we reach, what we're mapping to, that domain to. And then we have the range, which is the set of all images from the set A. So let me, maybe I just found actually in the source that I added the video that I told you to have a look at, I found that this actually maybe explained much more in more detailed example. Like, see here we have a function from A to B. So A is the domain and B is the codomain. Now look at here, for every function, for every value or element inside of A, we have something that is associated to it inside of B. So f of any element AI from A, AI is inside of A. So I'm going to have one unique B of I, it's a unique, but this f of 1 is actually B, which is unique, but f of 3 is also B, but it's unique. For every one of here, I have one element here. It would not be unique if I had like f of 1 is going to be associated, for example, to B and to A at the same time. So then it's going to be A and B. That's not going to be a function. That's not what we're talking about. We'd like to talk about, it's a unique when I have from the pre-image, I have only one image. That one image can have more than one pre-images, that's fine. But that's the idea. So now if we talk about these, this is the domain, this is the codomain. We said that, for example, for the image, B is the image of 1 under F. Actually, it's also, B is also the image of 3, but the 1, 3 is the pre-image of B under F. So because I was saying that B is the image of 1, so B is also the image of 3. So this is another sentence, is also the image of 3, which is correct. Now don't look at this for now, I'm just going to talk about it later. And then we have the pre-image, that means 1 and 3 is the pre-image of B, because 1 or 3 are the pre-image of B under the function f. Now this A, B, C are the images of f, which means, see, the domain, the codomain B has A, B, C, D, E. However, these two, there's no element from A that is associated to them. That means my images, the set of images, are only A, B, and C. That's all the possible images that I have here. Because even the codomain has more, but I'm only using, only associated to a few set of them. Okay, and what about the range? Well, check, the range is actually what we're talking about. These are the set of images. So what are all the possible images that I can have? This is the range. So the range is all the elements in the codomain that are an image of something from the domain. So let's summarize. The domain is the set we start from. The codomain, the set we are going to. If we have like a function f is from A to B. So these are the domain and codomain. Now the image is the element inside the codomain associated to something from the domain, and the pre-image is from the domain that is associated to some codomain. So if I ask you what is the pre-image of A, your answer should be 4. And if I ask you, okay, what is the image of 3, your answer should be B. So that's a short summary. You can have the put a link on the of that video in the bottom, even though that's one on the list over there. But this is the specific video talking about that. Okay, so let's see this example with the grades. So what are the domains and codomain and range of the function that assigns grade to students described in the first slide, which is this one. So what are the domains? Well, this is the domain, the set of all names of students. This is the codomain. So this is the domain. Okay, what about the range? So when we look at the range, what would be the range is all the images that have a pre-image. So for example, here A, we have a pre-image, which is Farhat. B, we have a pre-image, actually we have two, okay, which is Anas and Basim. What about C? We have a pre-image, which is Shaheen. What about D? Oh, no, we don't have any, so this is not going to be part of the range. What about F? F, it has one, that's Faraj, so that's actually the range is going to be A, B. Oops, I said it's something, I clicked too far away. Okay, and then C and F. So this is the range. And we can find here what we've been talking about. This is the answer. So the domain here is the set of all the names. They give it a name, they call it G. And then the codomain is the set of grades. I mean, this should have been G if I had to make a name. And then the range is the set A, B, C, and F, and D is not part of it because D does not have any pre-image. All right. Another example. Let R be the relation with ordered pairs. So we have this relation with these ordered pairs. Actually, I would have been nice if we could hide these. But I could. Let me just do it. Okay, just one moment. All right, let me control and print screen. Just copy this. And then let's go to here and paste. All right, so now if we have that, so let's R be the relation with ordered pairs. Each pair consists of graded students and the student's age. Specify the function determined by this relation. So the function is going to have, we have these pairs. That means what we need to do is you have to, what would be the domain? So for us, the domain would be, let me just do that in another color. Okay, can I increase a little bit? Brush. Okay. So the domain is going to be what? Abdul, I don't know what. Abdul, and then Brenda, Carla, Desiree, Eddie. I need to just zoom, go press down. So we have again, where's the Eddie and Felicia. Is that okay? I mean, don't always trust what I'm saying because sometimes I make mistakes on purpose, and sometimes I just make mistakes. Okay, so don't always just say yes to whatever I say. So double check what I'm saying, okay? So this is the domain. well, how do I know? Because this is from where we start, and this is the one that is going to be associated to it, is the 22, etc. So I'm just going to put the numbers. So we have 21. What are the odd numbers? I'm just going to put them in order. I don't have to, but let me put them in order. I may put them like in the order in which I see them. So okay, I have 22, 24, 21. Am I going to repeat 22? No, I have it here, so I'm not going to repeat it again. 24, same thing. 22 again, same thing. So I'm not going to repeat those. So this is my codomain. So that means 22 here is the image of Abdul. Abdul is the pre-image of 22. So now what I'm going to do, I'm going to represent it this way. So Brenda is 24, and then Carla is 21, Desiree 22. Let me just do it better. And then Eddie is 24, and then Felicia 22. And this is the representation of that function. And so the domain is that, the codomain is all the possible ages, which is the ones there, and then the set is, this is the codomain. So that's pretty much it. Okay, so these are other examples. I mean, I'm not going to go into all of these because we will have some of the examples there that we're going to be talking about them, but you get the point. So we have the domain. A function takes us from one domain to the codomain, and every element in the domain is called the pre-image, and everyone in the codomain is going to be the image. Okay, so we have some questions. What is the format of the question in the midterm? Okay, that was a long time ago. Format of the question in the midterm is going to be like the quizzes, except maybe you may have something to write more. Like for example, something that we didn't do in the quizzes is, okay, fill the truth tables, for example. Okay, so that's an example. You have to fill it, but it's same topics. So type of questions. No, it's not going to be a blackboard. I just said it will be on paper as all the exams, midterm exams, etc. The domain can share the codomain, but can be the codomain share the domain. I don't know what you mean by the domain share. There's no sharing. We don't share. We just have some transition from one to another, some mapping from one to another. So we map from the domain to the codomain. Now your question is, are you mentioning that am I mapping from the codomain to the domain? Well, maybe, but that's not going to be the same function. That's something we're going to call it actually the reverse of that function. We talk about it at the end of this course, this class, inshallah. So if this is what you mean. All right. Now, there's also the last two definitions we're going to be talking about. I mean, this is one of them: one-to-one functions, injection functions, or there's onto functions with this surjective. Sorry. So we'll talk about these, and this is going to be one of the last, among the last, one before the last definition we're going to be looking at, main one, I mean. So a function f is said to be one-to-one, or this one-to-one means injection. That's the same thing, just the way it is. Okay, it doesn't want to highlight. Okay, nothing works. Discard. Shift F5. Okay. So a one-to-one or injection, this is the same thing. So if and only if f of a equal f of b, that means that a is equal to b. So what we mean is that one-to-one is that if we have the image is the same, that means the pre-image is the same, which basically says that this is not a one-to-one. Why? Well, because of this. We said that it's one-to-one if f of, okay, let me just find a better place. If we have f of ns is equal to b, and then we have f of Basim is also equal to b. If we say that if f of ns is equal to f of Basim, what we mean is that this is, if it's going to be one-to-one, if and only if ns is actually the same as Basim, which is basically not the case. So what we mean is that if we want it to be one-to-one, we don't want to have such thing like this. Every one from the domain is associated to only one from the predomain, which is how the function works, but also every image from the codomain is going to have only one pre-image, and that's what makes it this one-to-one. So that's the example here. For example, we have these A, B, C, D, and we have these numbers. I don't know if I can move this around. Maybe make it more transparent, maybe later. Discard. Let's do that. Where is it? I'm trying to find it, but I'm not seeing it. Why is it this one? No, this one. Okay, so the background color. Maybe reduce the. Don't want it. Close settings. So it will close much faster. That will be better. So what we have here is that we have the every element in the domain. Every element in the domain is associated to only one in the codomain. And this is the one-to-one. If we have two elements from f of A, f of B, that means if we have two elements here, they're equal. Well, if two elements are going to be equal only if they're the same. So if I'm looking, this is to be 1. If 1 is equal to 1, that means A is equal to B. That means they have to be exactly the same. So here, that means in my case, it's going to be C. So that's what it means. So f takes on different values, and the 4 elements of its domain. This is just, I don't know what this is not mentioned in a way that is clear. So determine whether the function f from a, b, c, d to 1, 2, 3, 4, 5 with f of a is equal to 4, f of b is equal to 5, f of c is equal to 1, and f of d is equal to 3 is one-to-one. Well, how do we know? Is that we just make sure that for every one of these values, that if they are equal, that means these ones should be the same. But if they're different, that's actually all of them are different. That means it's one-to-one. So this is, let's see another example of one-to-one. Okay, so if we have this function that, okay, how did it go? We have this function which is f of x give us x squared from the set of integers to the set of integers, which means now we're asking as of, let me just control discard shift F5 control print screen. I just would like to have this. Okay, go back here. All right, so now what we would like to say is that we would like to have the function f, which is this one. That function f is going to be from integers. Well, remember this notation, right? From integers to integer. That means this is the domain, this is the codomain. And now what that function says is that if you give me an x, I'll give you the square of that x. Now, is this going to be one-to-one? Now, that means if I have like f of 2, this is going to be equal to 2 squared, that means 4. And what about f of minus 2? This is also 4. And we said if we have f of a is equal to f of b, it has to mean that a is equal to b. And clearly a is not going to be equal to b here. For us, a here is 2 and b is minus 2, even though f of a is equal to f of b, but a is not equal to b. So that means this is not a one-to-one. So that's the idea. To be one-to-one, that there can be no two values of x where f of x1 is equal to f of x2. But in this case, another example, if f of 1 is going to be equal to 1, f of minus 1 is also equal to 1, even though that 1 and minus 1 are not equal. So this means that this is not a one-to-one. However, if I changed the domain to this, if you remember, this means the positive integers. Now, if I change this to make it, instead of from all integers, only the positive integers, it doesn't matter if we also put positive here or not. But if I just make this, that means this minus 2 is not part of the domain, and any number is going to be having a different value for its square. There's no two numbers that are going to be having the same square. So this one, if the domain is changed, then this becomes a one-to-one. If not, if we leave it as from integers as it was initially said, so it is not going to be one-to-one. And okay, how about this? Let me just do this example 8. Try to, even though you might have seen it, but let's say determine whether the function f of x equal x plus 1 from the set of real numbers to itself, which means f is going to be f is going to be from the set of real numbers to real numbers, is one-to-one. So determine whether it is one-to-one. So is it one-to-one? Can I have like two numbers that are going to be equal? So this is my function here. Can I have two numbers that are going to be equal to this? Two numbers that are going to be the same but giving me the same value. So let's say, for example, if I put f of 0, this is going to give me 1. Can I have another f of some value y that is going to give me 1? Is this possible that this y is going to be equal to 0? If it's different from 0, I can have a y that is different from 0. That means, yes, it's possible. But if I can't, that means it's not possible. So let's have a look. If I have this, I'm going to say that I would like to prove that this is possible. I'm going to replace the x here with the y, and that means f of x is going to be x plus 1. Here, f of y is going to be y plus 1. That means in my case, this is going to be equal to y plus 1. So is it possible that I have 1 that is equal to y plus 1? So what kind of y is going to be making this possible? Well, all I have to do is put this 1 from here. So 1, okay, I just went too far away. So I just have now 1 and then minus 1 is going to be y, which means this is 0 equal y. So we just proved that if there's another number that has the same equal to, it's going to be 0. So they are the same. So this is going to be meaning that this is an example of a value that if I replace it, it's going to be actually exactly the same value. So if I have f of a is equal to f of b, then that means if and only if a is equal to b, that means that's going to give me the same this is one-to-one. I mean, that's what I wanted to prove. So that's the idea. So not two values. So we can use that by trying to do some different values that are going to be the same. Okay, hold on. In order for it to be, then there can be no two values of x where f of x1 is equal to f of x2. So different values, x1, f2 is equal to same. So this is not going to be possible. So if we find one, so it is one, such that f of x1, since f of 1 is equal to f of minus 1. Oh, we're talking about this, sorry, I just got lost. I was looking about here and then I forgot and I was looking here. So yeah, so if we have these two numbers, to prove that these are actually going to be exactly the same number, is that these, if we have these to be equal, that means these are going to be equal. And if we just remove the 1, so that means x equal to y. So no matter for what x is or what y is, this is going to be a one-to-one function. All right. Okay, so now the other one, which is the last one, the onto function, which is called the surjection. The onto function is actually the opposite of the onto. I mean, not in that case. I'm looking from, we start from, in the one-to-one, we start from A to B. Now, in the onto, I'm looking at starting from B. For every element B, there is an element A that is the pre-image of B. So that's what I mean. We'd like to prove that it's onto if, for example, if we have this here, this is not an onto, this is an one-to-one, not even one-to-one, because if I have these two, they have different, so this is not one-to-one. This is not an onto because it's not going to be, not all of them, all of these elements from a codomain have an element here. If we had one, then this means this is an onto. So let me go back here. So the onto function, that is, for every element of B, there is at least one or more element that is matching from A. So if we have something like this, this is the codomain, this is the B, this is the A. What we're looking for in the onto, or surjective, function that is surjective, that means we're looking for every element here should be having a pre-image. So it might be more than one, but at least one. And this is the definition of the onto. So now let's have some, let me just control print screen, copy this. Let me just, okay, up. Let me try to remove these. I just would like to remove these ones. I don't want to, I want to build that solution. This is just a distraction, and let's remove the solution again. Next time maybe I would remove them from there. All right, so let's have a look. Now, is the function f of x equal x squared from the integers to the set of integers is an onto. Where is this? Sometimes this thing disappears. All right. So is it an onto function? Now, which means for every element, now if I have f is from an integer to an integer, and we're saying that for every x, I have x squared. What I'm looking for is that if I have all the values from this set of integers, each one of them is going to be having an x that is going to be from the integers that is going to satisfy this function? Without looking at the solution, just, I mean, at the answer, can you just maybe write in the chat what do you think? Is this an onto? Yes or no? Yes, right? Everybody says yes. Yes, yes, yes. Great, great. So let me ask you this. That was a bit of a trap, I think. Let me be more specific. I'm just here. Let me control Z. Yeah. Now I said that from any element here, I need to find one that is actually the pre-image of it. Now let me tell you about this element, one element here where that is 2. 2 is part of all the integers, right? Now is 2 have some kind of pre-image that is going to be that x of is going to be 2. In other words, this is x squared is going to be 2. Okay, x squared going to be 2. That means my x is going to be square root of 2. Okay, so there is an x that can make my f of x equal to 2. That x is going to be f of square root of 2. But my point here, my question is this an integer? So that's not an integer, which means there is an element from the codomain. That element from the codomain does not have any mapping or any pre-image from the domain. It may have another, if I change this to make, okay, real numbers, then yes, you're right. But if I just asking you about from an integer to integers, the answer is going to be no. This is the time when you should have not listened to me. Sometimes I can trick you into thinking that's the right answer. So think for yourself. But anyways, we're here to learn, so that's fine. Making mistakes is part of the process. Okay, let's do the other one. Is the f of x equal x plus 1 from the set of integers to the set of integers again? Is this an onto? Which means if I have f of, let's use the same thing, f of x1 is equal to x1 plus 1. Now, do I have at least one value that is going to be an integer associated to this, every element in this integers? What would be the what would be your answer for this one? Let me just cancel this. So that means, is this an onto from an integer to integer, where this is the f of x plus 1? That means for every one number here, I can have a pre-image that is going to give me, just fulfill this condition. Onto? Okay, what about the others? It's not an onto, not into, because it doesn't apply on negative. All right, doesn't apply on negative. What do you mean? For example, if I have minus 5, can't I have some f of x that is going to be equal to minus 5? Well, let's have a look. Minus 5, that means x plus 1, which is, if I just look at this, that means x can be minus 6. And then if I have f of minus 6, how much does it give me? Minus 6 plus 1, that's minus 5. So I found that this minus 6 is still part of the integers. So yes. So you're mentioning that it's not because it doesn't apply to any negative. No, it applies also to the negative. I can find for every negative some number that is going to be following this. For every negative number in the set of integers in the codomain, I will be able to find the pre-image associated to it. Anybody says something else? So it's an onto? Yes? No? Yes? It looks like it's an onto. I think so, because we can find, because it's linear. This one is that means for every, if you give me x, I'm just going to give you the x plus 1. So if you look at any element that you give me, this is the all possibilities. This is 0, 1, 2, etc. And this is minus 1, minus 2, etc. because we're moving from one at a time. So f of x gives you the x plus 1. So the next one, if f of 0 give you 1, f of 1 give you 2, f of minus 2 gives you minus 1, f of minus whatever give you. So it's actually going to be applicable to every single one of them. So it is going to be an onto. All right. Okay, let's go back and see the results. So first of all, this is not an onto, yes, we agreed, and this is going to be an onto because every integer is going to be, there's an x that is going to give me that. And the way to prove, I mean, in general, the way to prove, for example, here is that we just prove that we find one that actually is two that are, some that are not part of the domain. Or for this case, we're going to find, let's say, if we can find one y that is going to satisfy this, and then if we find that this y is going to have some kind of way to find the x that is going to be dependent on that y, and if we do find that that x is also part of the domain, like not like what we had here, then that means that, yeah, this is possible. So for every y minus 1, if y is from the set of integers, y minus 1 is also an integer, so the domain of it is in the domain of f. That means this is an onto. In example 9, what about, because the function f in example 9 assigns jobs to workers, I think we skipped that anyways. Let's have a look. Suppose that each worker in a group of employees is assigned a job from a set of possible jobs which to be done by a single worker. In this situation, the function f assigns a job to each worker is one-to-one. To see this, if x and y are two different workers, then the job of x is going to be different from the job of y, because the two workers x and y must be assigned different jobs. Okay, so now the question is, this was in onto. Is this one-to-one? Sorry, is this now an onto? So what we're saying here is that every single worker is assigned a job from a set of possible jobs, each to be done by a single worker. So that means I have workers A, B, and C. These are workers, and I have jobs 1, 2, and 3. Now the question is, we said that each worker in a group of employees, is assigned a job. That means each one is assigned a job. But does it mean the job is unique? It's assigned a job, that means I don't have these two. But does it mean it's unique? It means just each one is assigned a job. It does not mean that each one from the codomain, each job from the codomain is going to be assigned to one of the workers. So, because here all it says is each worker in a group of workers is assigned a job. It doesn't say that each job is going to be assigned to a worker or more than one worker. So all it says is that we have a set of workers, A, B, and C, and this set of workers are going to be assigned a job. It does not say that it's being assigned a unique job. They all might be just doing the same job, and we have other jobs that no one is assigned to. But if we want it to be onto, we don't want these. That means we don't want to have some that are in the codomain that do not have any one assigned to. So the answer to that is not true. Because there may be, or there may be, actually it's not at least, there may be, because we don't know, it's just, so there may be at least one job that has no worker assigned to it. Okay, now the function f is a one-to-one correspondence or bijection if it's both one-to-one and onto. So if it's both one-to-one and onto, it's going to be the one-to-one correspondence are called bijection. I think they use bijection or bijection. I don't know which one they use. I can't remember now, but I think it's bijection or yeah. So let's say you have this f from the set of A to the set of B, where we have f of A. So let me just draw these. We have A, B, C, D, and then we have 1, 2, 3, 4. Now f of A gives me 4. Okay, that's not the best way. Let me just do it better. Now this is the A, this is the B, C, and then D. And this is 1, 2, 3, and 4. So now I have f of A. Well, imagine that A is a capital A. So this is A of 4. F of B gives 2. F of C goes to 1. And f of D is 3. Now this is 1 to 1 because for every element here we have only 1. So for every pre-image we have also only 1. So that's the 1 to 1. For every element from the codomain we have 1 that is associated to it, and this is at the same time 1 to 1 and onto. So this is what we call bijective. And why are we looking for this bijection? We're looking for it because the bijections functions can be reversed by doing this f minus 1 of a function. Now, that's the idea. So why do we looking for this type of situation? Is that because we have an application for that, and the application is that we can reverse that. So let's recap. We have domain and codomain. It's 1 to 1 if for every one of them here we have just one that is assigned to. It's not 1 to 1 in this example because we have two pre-images pointing to the same image, which is not 1 to 1. So we want it to be 1 to 1, and it's not onto as well, but this one is also onto because every single one of it in here is also associated to, it has a pre-image associated to it. So that's why it's 1 to 1 and it's onto. This is not 1 to 1 and not onto. It's not 1 to 1 because we have these two that have the same image. That's why this is not 1 to 1. And it's not onto because this one over here does not have any pre-image. So that's the reason behind these two. Okay, this one is 1 to 1 and onto at the same time. Again, because every single one has only one here, and everyone in the element of the codomain has an image. What about this one? This is 1 to 1 because everyone here has one single image, but it's not onto because I have some in the codomain that do not have any association, any mapping from the domain. So that's why it is not here, so it's not onto. Okay, this is surjective. Surjective is the same as onto because we can have here for every one of them here, but here this is not 1 to 1 because it's this one does not have any image. This one is injective because it's 1 to 1. That's what injective is, the same thing, or 1 to 1, but it's not onto because we have this value, this element of the codomain that has no pre-image. And this one is 1 to 1 and onto, and this is bijective, which means also this one is bijective as well. So if they are both, they are bijective. Now this one is 1 to 1 and not onto. That means it's what? Injective or surjective? Looking for what you write. Injective or surjective. So 1 to 1 means injective or surjective? Yes, injective. So injective is the one-to-one, and the onto, this one is bijective, so it has both. I don't know what's happening. All right. Okay, so we're almost done here. This is another example of function f that is onto. All elements of b are used, and then not all. This is not one-to-one because we have these two h and a pointing to the same element. This one is a one-to-one, but not onto because of this 6. It does not have anything, and so this is again same thing. And so this is again not one-to-one because we have two elements here pointing to the same, but it's onto because every element here has 1. All right, so another examples. Okay, so we can have a look at that, but this is what I'd like to finish with because this is the last part, which we're going to be talking about how to inverse functions. And these functions that are inversed are represented with this f minus 1, but this can only be applied to bijective functions. Let f be one-to-one correspondence from set A to set B. The inverse function of f is the function that assigns to an element b belonging to b the unique element a in A, such that f of A equal to b. The inverse function of f is denoted by f minus 1, hence f minus 1 of b gives you A. So when f of A gives us b, if we take this and f minus 1 of b, we will be able to go to A. And this can only be possible if they are actually f is invertible. It's invertible, and f can only be invertible if it's if it is bijective. Let's f be the function from ABC to 1 to 3, such as f of A is equal to 2, f of B is equal to 3, f of 1 is f of C is equal to 1. So we have A, B, C, 1, 2, 3. A goes to 2, B goes to 3, and C goes to 1. Now notice here, this is bijection. Now, is f invertible? And if it is, what is its inverse? Okay, its inverse, it's invertible, first of all, because it's a bijection. It is one-to-one correspondence. Well, not really. I mean, maybe there's something that we don't talk about, which is the onto. Now, if you had 4, for example, well, even though this is one-to-one, if it is one-to-one, is this inversible? Well, f of 4 is equal to what then? So we don't have that. So actually, I need to check if there's something missing in this the mentioning. I think the idea is that it's not only to one-to-one, it's also wanted to be onto. But let me continue. Now, right now, what's the inverse of this function? The f minus 1 of 1 is going to be equal to, well, just look at 1. That means I go from 1 to the, from the codomain to the domain. So if this is f minus 1 of 1 is going to be C, f minus 1 of 2 is going to be A, and f minus 1 of 3 is going to be B. So I'm just going back. So I just need to check why they're talking about one-to-one correspondence. Oh, okay, hold on. It's a one-to-one correspondence. This is called the bijection. So yeah, that's why I did not pay attention. It's not. They don't say it's a one-to-one. They say it's a one-to-one correspondence, which is, if you paid attention earlier, it says also this is the same thing we're talking about. It's a one-to-one correspondence. That means bijection. So I was actually focused on just looking at bijection. I did not read it carefully. So yes, as I was mentioning, it's working with bijections, and if there is, then I can find the inverse. Now if we have something like this type of here, f of, let me maybe do that again, same thing, just go here, go back to here, paste, and delete this, oops, delete this, I just would like to show it. So okay, if we have this f from a set of integers to a set of integers such that f of x is equal to x plus 1, first of all, is f invertible? So to be able to do that, I need to find out if it's a one-to-one correspondence, as they say, or bijection. That means, is it a one-to-one? It's a one-to-one. That means every single element of z, of this set of integers, every single element of the integers, every x in here, has a value in here, which is, yes, if x is an integer, x plus 1 is an integer, right? I hope so. Yes. All right. No, I don't want to go back there. So now, what about the opposite? Is every element that I have in the integers will have one that is going to be associated to it, that's going to be its image in there. That's actually what we did. We showed it in the example before, is that if we had f of x is equal to some y, and that y is going to be x plus 1, so what is the value of that y? So if I know that I have this y, and I would like to know if I can find an x that is going to be plus 1, give me that y, and definitively we can find that one. What is that x? Well, x is going to be this y minus 1. So you just give me that y that I want to know, and because for every y I can have an x that is going to be the y minus 1, that is also part of this set of the domain that I'm looking for. So which means it's a bijection. Now if it is a bijection, now how can I find the f minus 1 of it? So what is its inverse? Its inverse means I would like to find f minus 1 of x is equal to what? That means this, actually maybe let me write it separately, differently. This is going to be, if I would like to have f minus what the inverse of, if I'm going this one from x, it takes me from x, takes me to x plus 1. The f minus 1 is going to take me from x plus 1 to the x. Oops. All right, maybe get bigger. That means I can have, I would like to be able to find some f minus 1 that is taking me from this x plus 1 to maybe equal to the x. Now, this is how we find the inverse. No, actually, let me show you. How do we find the inverse of a function, no matter what the function is? So let's say I have f of x is equal to x plus 1. This is the one we'd like to do. Now that means f of x is going to be some y that I'm going to be having x plus 1. So the inverse of that would be that I would like to have the x where the y plus 1 is going to be the result. So which means now I'm looking for the y that is going to be the x minus 1, and this is actually the f minus 1 of x. It's going to be the x minus 1. So the inverse is, when we do that, let me just go back in time. Okay, so when we do that, we just rewrite these and we swap these x and y. So first of all, I need to write this in this type. That means every function. This f of x, I just replace it with the y, and then instead of looking for this, I'd like to look for this inverse. To be doing that, what I'm going to do is to swap these two. That means the x and y, I swap them. That means here is going to be x equals y plus 1. And then I need to isolate the y because I said that my y is going to be this f of x, right? So then because I swap them, when I swap them, my y is going to be now become the f minus 1 of x. So that's the idea. So now once I have this, to isolate the y, all I have to do is to do this x minus 1 is equal to y, and then this is actually the f minus 1 of x. Let's have some more examples and see how we're going to do that. So this, well, this is what, okay, let me just go back to what I did, and this is what they did. Look here. So what they did is just they replaced this with y. They said f minus 1 of y is equal to y minus 1, but it's the same idea. Sorry, but it's the same idea. So the f is has an inverse because it's a one-to-one correspondence. That means it has it's a bijection, so it can be inversed. So that's the first thing, and then the second thing is that to reverse that, we suppose that y is the image of x, so this is y image of x. That means f of x is equal to y. That's what it means. And then we replace f of x with y. This f of x, we replace it with y, and then we just isolate this x by moving the 1 to this side, so that becomes x y minus 1. This means the y is the unique element of the integers that is sent to y by f. Okay, that's another way to say that. And then we get it by f minus 1 is y minus 1. Okay, this is another way how to do that, but at the end, the f minus 1 of x is going to be x minus 1. Let me just remove that. X minus 1. Or if you write it like f of minus 1 of y is equal to y minus 1, that's exactly the same. It's just the way how you write it. That doesn't matter what the letter you use here, it's the formula that makes sense. Now let's have a look at this other one. Let's have this example 17. If we have this from this time, it's from the set of real numbers to the set of real numbers. And is this invertible? That means, do we have for every real number here a real number that is going to be the square of it? For every number that we take, can we square it? That's what this means. No, because of the power. That means, is there any x that I can find in this domain that I cannot have its square? Is there an x that can never be squared? Not sure though. So that means it's a one-to-one. That means for everyone from the domain, I can find that there's a unique x square of it. So whatever the x is, I can find what x square is, no matter what x is. But it's the onto now that is going to be the problem. Is if I have anyone that's from a codomain, every number, is this going to be like I have onto? That means I have only one to do that. Let's say, for example, 4, or there are many, but let's say 4 is 4 from this codomain. Am I going to find one element and only one from the domain that satisfies this? Well, no, because I will find that 2 square is giving me 4, and minus 2 square is also giving me the 4. So, which means this is not an onto. And this gives me that f is not invertible. So I cannot invert it, so there's no way for me to try to find what is its inverse. Because I only do the inverse once I know it's a one-to-one correspondence or bijection. That's the same thing. Now how to find the inverse? If you know that f is invertible, you have the f of x. I think this is why we swap. That is what I mentioned. We replace the f of x with the letter y, and then we swap x and y, since y has a yx partner, which means it can be reversed. Use algebra to solve the x and replace x with f minus 1 of y. Anyway, so let's have a look. So let's say find the inverse of f of x equal x plus 5. So we replace this with y. So that means we have this y, and then we swap. This is the actual thing, is we swap the x and y. So this is the part that is the tricky, that should not forget, and that's the key to find it. Once we swap this, all you have to do then is, when you swap that, you find that f minus 1 of that y is going to be y. So that's pretty much it. It's straightforward. So, but actually, this was swapped, and there's, I mean, a couple of things that I worked here. There's something weird that happened. Okay, so this, if I swap them, that means x is equal to y plus 5. So this was done is actually a fast step. So this step here, this is what I get. Step number 2, we need to swap. I mean, we replace the letter and then swap the x and y. So this is the letters, and we swap them. This becomes x equal y plus 5. And then if I swap these, replace f of x with the letter y, that's what we did. F of x replaces with the letter y. That's it. And then we swap x and y. We swap the x and y. Where is the x here? This is x becomes y. Whereas y becomes x, and we get this. Now, what we need to find out, I mean, this is kind of, there's a jump in here that's happening that is maybe making this not really clear. So what is happening now, after I swap these, actually I'm going to isolate this here. So this is going to give me this y is equal to x minus 5. So I just could put this plus 5 and put it to the other side. It becomes minus 5. And this is actually f minus 1 of x. So anyways, the way it was done here is not, I think, is maybe not as clear. If you understand it, that's great. I'm all good for it. Well, so let's have a look at this here again with the same way. So we have this. We replace this one with y. G of x is like f of x. Doesn't matter what's the name. They use g instead of f. It's not a big of a deal. So you can just use any letter that expresses that this is a function. So we replace this with y. We get this. And then see this here. So this is what the step 2 is actually the result of so many different things. That's why actually I want this to be this first part here was not very clear. Let's have a look at here what happens. So I'm starting from here. See, this is y is equal to x divided by x minus 1. So what we did is just we replace this with y, and now this is going to be swapped. So I'm going to multiply this here. So it's going to give me y, this is equal to y x minus 1, which is xy minus y. So this is the idea behind this. This is equal to 2x. I hope I'm not going too fast. Okay, let me just go back here. I'm not sure that everybody's following, so just pay attention, because this is the trickiest thing that we have this today, and after this we do some exercises and we're free to go. All right, so I want you just to make sure that you're with me so you don't get confused. So what will happen here is that I replace j of x with y. This is the result, right? 2x divided by x minus 1 to x divided by x minus 1. Now here, what I'm going to do is I'm going to multiply by x minus 1. So I'm multiplied by x minus 1 here and multiply by x minus 1 here. So this is going to effectively cancel this here and then put it like this. Then if I distribute x or y to the x and minus y, this is what gives me xy minus y is equal to the 2x that was there. Everybody's happy with this? So far, so good? Yes? All right. Now that I have this, I'm just going to this y, put it on this side, and okay, because they just would like to, I mean, that's another way. I don't know why they did it this way. I would have done it differently. I would have, anyways, let's have a look. Because they would like to get the x together, I would have done the x together anyways. So they did it this way, which is not as straightforward. What I would have done is that from here, I'm just going to put 2x minus xy is equal to minus y, right? I just moved this one, moved it here. So when I move it, it becomes negative. So this is, I'm going to get the same result, but I'm just showing you what I would have done. So I just moved these to put the x's on, try to put the x's on the same side. So now this is minus y. I'm just going to make it plus y by just making this minus, and this is plus. Not a problem. Okay, if I'd like to make this x, I factorize the x. That means it's y minus 2 and equal to y. It's actually minus 2 plus y, which is y minus 2. That's the same. And then this gives me x is equal to y divided by y minus 2. And that's what they end up here, right? So this is this, and that is this. Something similar. But they did it in a way that, anyways, that's another way to do it. It's just an additional step that I'm not sure why they did it this way. But it's not a big deal. So what they did is put this y here, and then they moved this x here, just to move them around. Anyways. So at the end we get this, and this is actually this j minus 1 of y. This is going to be here. Because if we have f of x equal y, f minus 1 of y is going to equal x. That's the idea. So that's why if we have this y here, this is going to be this j minus 1 of y. This is our x. Okay, let's try to do some exercises. This is going to help us. Oh, I forgot about those. Yeah, but I think this is something that you might already know, but let's make sure that we just understand these. These are like some specific function, the floor and ceiling. These functions, actually, they have this type of denotation that is actually very intuitive. You see like a bracket when the top is not there and just the bottom is there, or the other side, actually the top is there and the bottom is not there. So when we say that this is the bottom is there, that means we're looking for the floor, which is the floor, the lowest thing. And when it's the bars are high, that means we're looking for the ceiling, the highest thing. So now what are these two functions do? So if we have this, the floor of any number is going to be the closest, for the floor, for example, this is going to be the smallest number that is going to be the integer that is less than equal to that number over here that you're given. So if you give me an x, the x can be anything. It can be a real number, integer, whatever it is. So x can be, for example, a real number. It can be an integer, but it makes more sense with the real numbers as a quotients, with actually 0 point something or point something. But if we have, for example, for some ceilings of 3, or this is going to be equal to floor of 3 or ceilings of 3, these are going to be exactly the same as this is 3. There's nothing that changes, but it makes more sense when you have 3.5 or 3.7. And now if we do this 3.5, the ceiling of it is going to give me 4. If it's not the ceiling, if it was now the floor of it, flooring of this is going to be 3. So this floor or ceiling, they always give me integers, right? That's why it's the largest integer, or the smallest is the smallest integer. We're just talking about integers. So that means if I have this 0.5, this 1 divided by 2, and the floor is going to be the smallest integer that is going to be next to this. So the floor, when the floor, that means we go down. So 0.5, the floor, we just look at the smallest integer that respect this is going to be 0. If it was the ceiling, 0.5, and this is going to be 1. Actually, it's just right here. So this is the floor, this is the ceiling. What about this? The floor of minus 0.5 is going to be the floor of it. That means it's going to be the smallest number, that is going to be minus 1, not 1. Well, because it's a negative number. It's the smallest number of below that. And for the ceiling is going to be the biggest number, the next biggest number based on that. And which makes it's much more easier with we have these numbers. So either it's going to be, for example, 3.9. I'm looking for the floor. 3.9 is going to still be 3. So whatever it is going to still be 3. Yes. How can the ceiling of one point? Oh, okay, the ceiling. All right, let me go back. All right, Control A, delete. So 0.5. If I look at the ceiling, so I'm looking at the biggest, the next biggest integer. So we have 0.5 is between 0 and 1, right? So this is 0.5. If I'm looking for the ceiling, I'm looking for the biggest one. Next, the biggest integer, then it's going to be the first biggest integer next to this value over here. So the next biggest integer is going to be 1. If I'm looking to the floor, that means the smallest next integer that I can find is the 0. So 0.5, the floor of it gives me 0. 0.5, oops, 0.5, the ceiling of it is going to give me the biggest number that is going to be there. Is that okay? How can the ceiling be? So, all right. Okay, so I forgot about these two, but basically, well, I don't want to get into too much of those, but the bits, etc. But we can get into that later. But let's have some exercises, and these functions are actually some basic things. Actually, these are some. If you use the math class in Java, you have this math.floor, math.ceiling that does this type of work. Okay, why is f not a function from R to R if f of x is equal to 1 divided by x? The question is, why f is not a function? What would be your answer for this one? Why f is not a function from the set of real numbers to the set of real numbers? That means the domain is the real numbers and the codomain is the real numbers. Domain not 0. I didn't get that. What do you mean domain is not 0? Because of the 0 is not part of. Yeah, you're right. I mean, because domain not 0, then, I mean, 0 is not part of the domain. Yes, you're right. Because if we have f of x, f of 0, with x is equal to 0, can we have 1 divided by 0? No. So that means it's not going to be like is not going to have any value for that. And this is actually what you meant, probably domain not 0, and because it's under undefined at 0, yes, and because of the 0, yes, because of the 0. That's the actual problem. Okay, what about, yes, the next one is because of the negative numbers. The next one is because of the negative numbers. Yeah, all right. The negative numbers are because if you have f of -1, it's going to mean that square root of -1, which is not a real number, right? Because of negative numbers, yes, because of the negative numbers. It's not defined, yeah. And how about this one? F of x plus minus of square root of x squared plus 1. Because each x value has 2 outputs. Yeah, so it has more than 1, so it cannot be a function because it's not 1-to-1, because it has plus and minus. So it cannot be a function because it has 2 distinct values for every x. Okay, what about, it's a good job for that one. Okay, find the domain and range of these functions. The function that assigns to each bit string the number of ones in the string minus the number of zeros in the string. Okay, sorry, I just almost destroyed my microphone. All right. Is it still working? Can you still hear me? I hope yes. Yes, okay, good. All right, the function that assigns to each bit string the number of ones in the string minus the number of zeros in that string. So if we have a string of 10110001, is going to assign to each bit string the number of ones in the string minus is going to be minus the number of zeros in the string. So this is going to be a number of ones, 1, 2, 3, 4. So 4 minus 1, 2, 3. This is going to give me 1. So the question is, what is the domain and range of these functions? And honestly, this is kind of a bit of a stretch, because the strings can be actually very much in sequence of zeros and ones. So the set of bit strings. So this is actually not really a good clear example, because the set of bit strings can be very vague. Yeah, sequence of zeros and ones. And the range is all possible integers. The set of integers, well, not maybe necessarily, because if we do the subtraction, we might not all have. Okay, forget about this one. I don't like this example. This exercise. The function that assigns to each bit string twice the number of zeros. Also these bit strings, the leftover. Okay, forget about those. All right, these are not really very clear examples, because again we're going to say the set of bit strings and then the range is okay, forget about that. Let's have a look at find the domain and range for these functions. The function that assigns to each pair of positive integers the maximum of these two. Okay, so these ones, okay, we can just talk about find the domain and range of these functions. Now remember, the domain is actually from the first set that we start from, and the range is actually all the values in the codomains that are going to be associated from every single one of the values from the domain. So let's talk now for the function that assigns to each pair of positive integers the maximum of these two integers. So what's the domain here? A pair of x and y that is actually from the pair of its positive integers. So it's not going to be r. So it's going to be the pair of all integers. This is the pair of all integers. So from z and z. And this is going to be mapped to the maximum of these. So the maximum of this is going to be of what range? Can I say like all these as all the integers? Or is it like, can I stop at some particular one? I mean, I'm thinking that the range should be this in the set of integers. Is that right? Okay, what is it? Each pair of positive. Oh, sorry, I forgot to. I didn't pay attention to the positive integers. So positive integers. So this is the domain. Okay. All right. So that's a good point. You remember this, right? Yeah. Okay. Z plus. This is the. What is it called? Can you tell me the name of that thing? This one over here. Someone can remember? We've seen it in the sets. We start talking about the set of integers. No, it's something about the product. Cartesian product. You remember the Cartesian product? When if you have a set of A, B, C in one set and the set of 1, 2, 3. So if I have the Cartesian product between the two, that means I'm going to have the pairs A1, A2, A3, etc. B1, B2, B3, C1, C2, C3, etc. Remember that? Yes, the Cartesian product. Good. So that's actually, this is the domain, because this is the set of all possible pairs. Each pair of positive integers. So to have this positive integer, that means I'm going to have 0 with 0, and then 0 with 1, 0 with 2, 0 with 3, and then etc. And then 1 with 0, 1 with 1, 1 with 2, etc. So this is all the possible pair of positive integers that I can have. And then the maximum is going to be the positive integers. So that makes sense. Is that okay? Everybody understand this? Yes, yes. Anyone has any question? You're very understanding everything. So either it's actually true and alhamdulillah, everything's great, or there are some questions that you don't want to ask. Okay. Again, this function of bit of strings to the number of times the time the block 11 or 11 appears. So how many times the number 11 appears? Okay, I'm not a big fan of these type of questions, and yeah. So the number can be 0, 1, 2. It depends on the set of strings. So this is function that assigns to a bit of strings. I'm not going to be a fan of those. Okay, consider these functions from the set of teachers in a school. Under what condition is the function one-to-one if it assigns to a teacher his or her office? So I'm going to consider these functions that set a teacher in a school, that a set of teachers in a school. Under what condition this function is one-to-one if it assigns a teacher to an office or to an assigned bus, to chaperone in a group of buses taking students on a field trip, or to national ID card. So if I'd like to have teachers, a set of teachers, chaperone is, I don't know what does it means explicitly, but I think based on the context that there's going to be like supervising a group of buses taking students to a field trip. But okay, let's just go for just the first one. Let's say the office. So I have a set of teachers, A, B, C, and then now I have a set of offices, office 1, 2, and 3, or 4. Now, under what condition is the function one-to-one if it assigns to a teacher his or her office? Great. If one has actually one office, if we have like one that has 2 offices, not only that, it's also that every office is assigned to only one. Like if we have like two teachers, if we say that each teacher has one office, that's true, but it's not complete, because we also would like to have that each office has only one teacher, right? So we'd like to have each teacher has an office and each office has a teacher. Now if you have something like this, we don't want to have that, and because if it's not on two, it cannot also be bijection. So yeah, well, the teachers share offices, so yeah, it has to be an office if they don't share offices. Assign bus to chaperone. So again, if they're not more than one teacher per, want to assume only one is per bus. And then for the national card, how about that? So if we have this set of teachers and they're assigned the national ID card, is this going to be a function? Well, yes, because it's going to be one-to-one and onto. So there's no two people having the same national ID, and that's the and everyone has a national ID. Okay, so this was actually a little bit too basics, a bit confusing at some points. Yeah, if a teacher is okay, each person has a national card. Yeah, all right. Okay, how about these? Determine whether each of these functions from A, B, C, D to itself is one-to-one. Now this one over here, is it a one-to-one? Now to know it's one-to-one, what I need to do is, this is from ABC to itself means I have ABCD to ABCD. And I want it to be one-to-one, that means I need to look that for everyone here, it just assigns one. So from f of A is going to B, f of B is going to A, and then f of C is going to C, and f of D is going to D. Is this a one-to-one? This first one looks like it, right? Okay, now let me just remove these and look at the next one. F of A gives me B. F of B goes to B. F of C gives me D. And F of D goes to C. Is this a one-to-one? Yes, no? Okay. Now we have yes and no. So we need to have more people leaning towards one side of the other. So it's no, it's not one-to-one. What is the condition for it to be one-to-one? Let's just jump back a little bit and remember the definition of one-to-one. So one-to-one means if the image is the same, that means the numbers, the pre-image are the same. Which, in other words, what we don't want to have is like for the same image, we have two pre-images that are pointing to it, because we want that if this image is equal to another one, that means the values are going to be equal to another one, and we don't want to have them both. Now in this case, we just okay, we just have this B that has A as a pre-image and B as a pre-image. So if we find out that the same number is the result of 2, that means it's not going to be, so it's not going to be one-to-one. So it's not an injection, not one-to-one. Okay, what about this other one over here? Let me just remove this. And actually it's easy to answer it once we draw it, but we don't have to draw it all the time. As soon as you see, for example, the same value in two different functions, then you can say that it's not going to be possible. But let's draw that and see. F of A gives you D, f of b gives you b, f of c goes to c, and f of d goes to d. So now, again, we have the same problem. All right, so nut and nuts. Okay, what about this? Whether each of these functions from z to z is an onto. Remember, onto means that if I have a, b, c, and 1, 2, 3, 4, I just make sure that each one of them has to have, each one of here, it has at least one. It may have like two, but at least I have one. Now let's have a look at these over here. This is not a function. Okay, determine whether if this function from z to z is onto. I mean, I'm not asking if it's a function or not a function. I'm talking about if it's onto. So you're saying that this is not a function? Is that what you mean? Or this is not an onto? I mean that A, B, C, 1, 2, 3, 4 example. Oh, okay, yeah, right. Don't forget this is not. Yes, you're right. That was not a function at all. Yeah, but I was just focusing on the onto part. That's all right. So now, what about this one? This A, is this an onto? Onto, the phone is onto. Why? Because we can find for every number that we can find there's only one number. At least one number is going to be giving me that result. So yes. Okay. So this onto, since all elements in B are used in B. What is B? I mean, probably they mean B is the function is from A to B. I think that's what was meant from here. Okay. What about this one? N squared plus 1. Is every number is going to be, it's not an onto. And why is it not an onto? I mean, it looks like maybe it's an onto. Because what we say is from Z to Z, right? So can I find some number that is going to make any n that gives me this n squared plus 1? Remember that n is from set of integers, and this should be set of integers. So if I have f of, let's say, minus 1, this is going to be 1 plus 1, which is 2. F of 1 is going to be 1 plus 1, which is 2. But again, I'm not asking about from 1 to 1, but I'm asking about onto. That means I have 2 that is going to be associated to minus 1, and 2 also associated to 1. But is there a number that I can find, one of the numbers that cannot have any number associated to it? Because of the power, the root of 35? What do you mean by the root of 35? I don't get it. Because 35, I mean, we need to find, if I go, for example, to f of, okay, why it's not writing? Oh, sometimes it bugs like this, I have no idea why. Okay. Anyways, okay, discard. F5. So we said that, okay, here this one, this is an onto, okay, but this one is, we're looking for that every element from the set of integers, it has some kind of a number from another integer that is going to be giving me this. So we said because the power, the root of 35, the root of 35 is not an int, so that's why if you're talking about this again, Okay, so this is not helping. All right, actually this is not an onto, because not every value in Z is going to be found based on this, is going to be respecting this condition. Okay, what value may not be? Well, how about in the set of output of integers, I have 0. Can I have 0 here? Can I have this to be equal to 0? So 0 is one of the elements of the integers that is going to be on the codomain. So I need to find that all these elements has a value that is going to be in the domain associated to it. Now if I have something like this, that means n squared plus 1 is equal to 0. That means n squared is equal to 1. That means n is equal to square root of 1, which is, yeah, it makes sense. Square root of 1 is what? Isn't it 1? But what about 1? Or is there a value? I think I remember that there was supposed to be value. There's a mistake. This looks like there is a mistake. Yeah, I think there is a mistake, because since there is no element in the domain that maps to 1, well, yeah, there is. But actually not 1. I think maybe, can I have 2, for example? Yeah, I have 2. If with n is equal to 1, it's going to have 2. Can I have 1? Can this be equal to 1? That means n squared is equal to 0, which is n is equal to 0. So it's possible, because this is not z plus. If it was z plus, yeah. But I think you're right. There's a mistake here. This is an onto. And there is an element domain that maps to 1. Okay, I need to double check that. All right. Okay, what about this one? Now again, I need to check that every element in the integers that are going to be here will have something that is going to be the square root of that number. That is going to, it's not square root, so not square root. I don't know. I just forgot the name of that. So n of the power of minus 1/3. That's actually the equivalent of not square root. This is the cubic root of n. And this, it's not always guaranteed that we have a number that is going to be part of the integer. So this one, I agree that it's not going to be an onto. Not an onto, because you cannot find 7, for example. Yeah, 7. Actually, there are many numbers that are going to be actually those. Okay, what about this? Remember, this is the ceiling. That means the biggest number of this n divided by 2, and then you get the biggest integer that is going to be next to that. So if we have this, let's check out all the elements that are the numbers here. Can we find an n that is going to be respecting that? Onto. Is there a number that this cannot be an integer? I think this is going to be an onto, because it's always going to be, because this is going to give me an integer, so this is an int. So that means every int that I have, 0, for example, can be the ceiling of something. So what is going to be the ceiling of this? If I want, what kind of n that is going to give me that this is the ceiling of n divided by 2 is give me 0? Minus 1. Yes, minus 1 divided by 2. This is going to be 0.5, and the ceiling of that is going to be the 0. Right. So I think this one is an onto. Okay, determine whether each of these functions from A to itself is surjective on onto. Okay, we did that. Let me just move to others, because we have some other questions. Oops. Let f be this function from an int to the int, and f of x is equal to 3x plus 2. Prove that f is injective. That means one-to-one function. How can we prove that f is injective? That for every x is going to be having a value that is going to be also int. Well, if x is an int, 3 times the x is also going to be int. 3 times the x plus 2 is also going to be an int. So this is just multiplying by an int and adding just int. So this is going to be int. That means for every int that I have, I will be able to have an f of that int, and this is going to be correct. So I don't know if they have something different. So I think the thing is maybe, okay, they're going to prove it by using a different, okay. So that would have been better. So that means we're going to use the definition that if f of a is equal to f of b, I would need to find out that at the end that a is equal to b. Okay, so that means this is 3a plus 2 is equal to 3b plus 2. That's actually more academic, which means remove the 2, divide by the 3, it is going to give me a equal to b. So this is actually showing that if I have fa is equal to fb, that means a is going to be equal to b. And I think that's what they've seen here. So if assumed fa is equal to fb, this follows that 3a plus 2, which is replace here x with a, is equal to 3b plus 2. By subtraction 2, by divided by 3, and then that means if a is equal to b, then f of a is equal to, okay, that means, I mean, I think they mean then a is equal to b. There's a mistake here, that a is equal to b. So there's a mistake here. I need to correct that. So we conclude that only if a is equal to b. Okay, how about this one? Defined by fx, and we prove that it's one-to-one. Okay, same idea. If we have f of a is equal to f of b, that means a square equal to b square, and with a square root, both of them is square root b square. This is going to give us that a is equal to b, and that's the, again, same proof. So that's the idea. Oh, yeah, I made a mistake. It's modern time now. I made a mistake, right? Because once we have this, this can be, because minus 2 is square is going to be equal to 2 square. It does not mean that they're going to be equal. Yeah. So actually just right here, this is going to give this plus minus a. So however, this does not show that a is equal to b, because a can be equal to plus b or to minus b. And this is actually not injective. Yeah, that's right. I made a mistake. Yeah. Yeah, true, correct. That's the problem. I didn't pay attention to that. Okay, let's try to move on. Can't again. All right. Okay, and we're almost done, I think. Yeah, we're almost done. Just maybe should have 5. Okay. Let's do this because I just want to make sure that people understand these. So again, this 3 divided by 4, 3/4 of a number, this is going to be equal to what? 3 divided by 4 is equal to 0. What? $75? Is it? It's 2 plus 1 divided by 4, which is going to be 2 divided by 4 plus 1 divided by 4. This is 0.5 plus 0.25. This is going to be 0.75. Okay, so this is the ceiling of 0.75, which is equal to, exactly, so this is equal to 1. What about here? 7 out of 8. This is going to be, again, this is the floor. The floor, I don't need to calculate this because the floor, I need to get the lowest integer that's going, this is, for sure, this is 0 point something something. So the floor is going to be, don't need to even count. This floor is going to be 0, right? Okay, minus 0.75. And I want the ceiling of that. The ceiling, that means the smallest int, and it's going to be the ceiling, that means the biggest. So let's have a look at this. Minus 0.75 is between 0 and minus 1. Now, which one is the biggest? Because the ceiling would like to go for the top, the ceiling, the biggest. Between 0 and minus 1, which one is the biggest? That's the ceiling. So that means it's the 0. That's going to be the 0. Correct. Okay, what about this one? The floor of minus 7 divided by 8. Sorry, the floor. Okay, I don't want to. So this is going to be, yeah, minus 1. Yeah, that's it. How about 3? The ceiling of 3, well, it stays as the same. The ceiling, if it's an int, it stays as it is. There's nothing that changes. Now this one is a nice combination of half plus 3 divided by 2 as the ceiling. Okay, so 3 divided by 2 is like 1.5, right? So this is 1.5. The ceiling of that is going to be equal to what? 2. Great. So this is 2. This is, then I would like to have the floor of 2.5. Because this is 0.5 plus 2, that means the floor of 2.5, which is going to give me 2, right? Because this whole thing is equal to 2, right? Let me just erase this. So this, we just calculate that this is 1.5. The floor of 1.5, sorry, the ceiling of 1.5 is going to give me 2. So this whole thing is 2. Now 2 plus 0.5 is 2.5, and I would like to have the floor of 2.5, that's 2. Now same thing here, this is the floor of 2.5, because 5 divided by 2, that's 2.5. The floor of it is going to be, this is going to be equal to 2. The floor looks at the smallest, 2. Then this 2 multiplied by 0.5, this gives me 1. So this is actually the same as asking what is the floor of 1, which is 1. I think that's what we did. And yeah, the inverse, the last one, inverse. I just would like to do this one and then let you go. Not the first one, I'm just going to go for this one. Find the equation of the last one. So remember, if we would like to do this, all we have to do is to do the swapping. I just would like to make sure that you do that. So x is equal to 3y minus 2. And then this is going to mean that x plus 2 is equal to 3y, which means that x plus 2 divided by 3 is equal to y. And this is the f minus 1 of x is going to be this x plus 2 divided by 3. So this is the inverse of that. And all right, so x plus 2 divided by 3, that's what I did. Okay, so then I'm just going to stop here if you don't have any questions, because you can do these exercises to make sure that you do things, you're able to do them without getting confused. Again, the same thing that you have to do is to replace this x, swap the x and y. We swap their positions, and then you can do the same for the others. So for example, let's do this last one in case this is not clear. So x is going to be minus 5y minus 7. And all I have to do now is to isolate the y. So this is x plus 7 equal minus 5y, which gives me y is going to be minus x plus 7 divided by 5. Or is it? the minus becomes a plus actually, so that's the plus. This is going to be the equivalent. The f minus 1 of x is going to be x plus 7 divided by 5. Or it can also, it's f minus 1 of y is equal to again y plus 7 divided by 5. So is that, I said y minus 7, this is plus 7, they put it here. Okay, so that's, I think we did it the same way. It's just like it's expressed differently. So here what I did is I said that this is going to be x equal minus 5y minus 7, which is going to be x plus 7 equal minus 5y, and that means y is going to be, I'm divided by, actually I made a mistake, I need to divide by minus 5. So dividing by minus 5, that gives me x plus 7 divided by minus 5, which is actually y is equal to minus x plus 7 divided by 5, or it's going to be minus x minus 7 divided by 5, so which is minus x plus 7. This is actually, this is the right one, so this is what we got. I thought we did I did something wrong, but no, it looks the same. So that's pretty much it where I'm going to stop at. If you don't have any questions, you're free to go and try to catch the Jama'ah if you can. If you have any questions, yes, you're free to ask.